Welcome to this comprehensive mathematical exploration. Today, we'll dive deep into two fundamental concepts that are essential for advanced trigonometry and calculus: the cotangent quotient rule and trigonometric identities. First, we'll explore the cotangent function. In a right triangle, cotangent is defined as the ratio of the adjacent side to the opposite side. This is one of the six fundamental trigonometric functions. We'll then apply the quotient rule from calculus. This powerful tool allows us to find the derivative of any function that can be expressed as a ratio of two other functions. Next, we'll explore trigonometric identities, mathematical equations that are true for all values where both sides are defined. These fundamental relationships help us simplify expressions and solve complex trigonometric equations. Understanding these concepts is crucial for several reasons. They provide the foundation for simplifying complex expressions, solving equations efficiently, and tackling advanced problems in calculus, physics, and engineering. By the end of this video series, you'll have a solid understanding of cotangent, master the quotient rule application, and be comfortable working with trigonometric identities. We'll work through everything step by step with clear examples and visual explanations. Are you ready to embark on this mathematical journey? Great! In the next section, we'll dive deeper into the cotangent function and explore its fundamental properties. Now we'll explore the cotangent function, one of the six fundamental trigonometric functions. Understanding cotangent is essential for mastering trigonometry and calculus. Let's start with a right triangle. We have a right angle here, and we'll focus on this angle theta. In trigonometry, we define cotangent in terms of the sides of this triangle. First, let's identify the sides relative to our angle theta. The adjacent side is next to the angle, the opposite side is across from the angle, and the hypotenuse is the longest side opposite the right angle. The cotangent of an angle theta is defined as the ratio of the adjacent side to the opposite side. This is the fundamental geometric definition of cotangent. Now let's explore the algebraic representation of cotangent using sine and cosine functions. Mathematically, cotangent of x equals cosine of x divided by sine of x. This formula connects cotangent to the two most fundamental trigonometric functions. Cotangent also has an important reciprocal relationship with tangent. Cotangent of x equals 1 divided by tangent of x. This means cotangent and tangent are reciprocal functions. Remember that tangent equals sine over cosine, which confirms why cotangent equals cosine over sine. They are indeed reciprocals of each other. Now, let's work through some examples to see how cotangent works with specific angle values. For our first example, let's find the cotangent of 30 degrees. We'll use the formula cotangent equals cosine over sine. We start by writing cotangent of 30 degrees equals cosine of 30 degrees divided by sine of 30 degrees. We know that cosine of 30 degrees equals square root of 3 over 2, and sine of 30 degrees equals 1 over 2. Substituting these values, we get cotangent of 30 degrees equals the fraction square root of 3 over 2 divided by the fraction 1 over 2. When we divide fractions, we multiply by the reciprocal. So we get square root of 3 over 2 times 2 over 1, which simplifies to square root of 3. Excellent. Now let's try a second example with a different angle. For our second example, let's find the cotangent of 45 degrees. This is a special angle with interesting properties. We start with the same formula. Cotangent of 45 degrees equals cosine of 45 degrees divided by sine of 45 degrees. For 45 degrees, both sine and cosine have the same value, square root of 2 over 2. This is what makes 45 degrees special. Substituting these equal values, we get square root of 2 over 2 divided by square root of 2 over 2. Since the numerator and denominator are identical, any number divided by itself equals 1. Therefore, cotangent of 45 degrees equals 1. Perfect. Now let's try one more example using the reciprocal relationship with tangent. For our third example, let's find cotangent of 60 degrees using the reciprocal relationship with tangent. We use the reciprocal relationship, cotangent of 60 degrees equals 1 divided by tangent of 60 degrees. We know that tangent of 60 degrees equals square root of 3. Substituting this value, we get cotangent of 60 degrees equals 1 divided by square root of 3. To rationalize the denominator, we multiply both numerator and denominator by square root of 3. This gives us square root of 3 over 3. These examples demonstrate the key relationships of cotangent. Remember that cotangent equals cosine over sine, and it's also the reciprocal of tangent. These fundamental relationships will be crucial as we move forward to explore derivatives and more advanced applications. The quotient rule is a fundamental technique in calculus for finding derivatives of functions that are expressed as ratios or fractions of two other functions. When we encounter a function that is one function divided by another function, we cannot simply find the derivative by dividing the derivatives of the individual functions. We need a special rule. Consider a function y equals u divided by v, where both u and v are functions of x. To find the derivative of this quotient, we use the quotient rule. The quotient rule states that the derivative of y with respect to x equals v times the derivative of u minus u times the derivative of v, all divided by v squared. Let me break down each component. V is the denominator function, u is the numerator function, du dx is the derivative of the numerator, and dv dx is the derivative of the denominator. For our first example, we'll find the derivative of f of x equals x squared divided by x plus 1. This is a straightforward application of the quotient rule. First, we identify our functions. U equals x squared, v equals x plus 1. The derivative of u is 2x, and the derivative of v is 1. Now we apply the quotient rule. F prime of x equals x plus 1 times 2x minus x squared times 1, all divided by x plus 1 squared. Expanding the numerator, we get 2x squared plus 2x minus x squared, all over x plus 1 squared. Combining like terms in the numerator, our final answer is f prime of x equals x squared plus 2x, all divided by x plus 1 squared. For our second example, we have a more complex function. G of x equals 3x plus 2 divided by x squared minus 1. We identify u as 3x plus 2, v as x squared minus 1. The derivative of u is 3, and the derivative of v is 2x. Applying the quotient rule, g prime of x equals x squared minus 1 times 3, minus 3x plus 2 times 2x, all divided by x squared minus 1 squared. Expanding the numerator, 3x squared minus 3, minus 6x squared minus 4x, all over x squared minus 1 squared. Combining like terms, our final answer is g prime of x equals negative 3x squared minus 4x minus 3, all divided by x squared minus 1 squared. For our third example, we'll find the derivative of h of x equals sine x divided by cosine x. You might recognize this as the tangent function. We identify u as sine x, v as cosine x. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Applying the quotient rule, h prime of x equals cosine x times cosine x minus sine x times negative sine x, all divided by cosine squared x. This simplifies to cosine squared x plus sine squared x, all divided by cosine squared x. Using the Pythagorean identity that sine squared x plus cosine squared x equals 1, we get h prime of x equals 1 over cosine squared x, which is secant squared x. Remember these key points about the quotient rule. Use it when you have one function divided by another. The formula is v times u prime minus u times v prime, all divided by v squared. Always square the denominator, and remember that order matters in the numerator. This rule is essential for finding derivatives of trigonometric ratios like cotangent. Now we're ready to apply the quotient rule to find the derivative of cotangent. This is where our understanding of both cotangent and the quotient rule comes together. First, we need to express cotangent as a quotient of two functions. Remember that cotangent is defined as cosine divided by sine. Next, let's recall the quotient rule formula. If we have a function that is u divided by v, then the derivative is v times d dx minus u times dv dx, all divided by v squared. Now we identify our u and v functions. In our case, u equals cosine of x and v equals sine of x. Next, we need to find the derivatives of u and v. The derivative of cosine x is negative sine x, and the derivative of sine x is cosine x. Now we're ready to substitute these values into the quotient rule formula. Let me clear the screen so we can focus on this crucial step. We start by writing the derivative of cotangent using the quotient rule structure. We have sine x times the derivative of cosine x minus cosine x times the derivative of sine x, all divided by sine x squared. Now we substitute the actual derivatives. The derivative of cosine x is negative sine x, and the derivative of sine x is cosine x. Let's simplify the numerator step by step. Sine x times negative sine x gives us negative sine squared x, and cosine x times cosine x gives us cosine squared x. This gives us our final unsimplified form. The derivative of cotangent x equals negative sine squared x minus cosine squared x, all divided by sine squared x. In the next section, we'll see how this can be simplified further using trigonometric identities. To summarize what we just accomplished, we successfully applied the quotient rule to cotangent by expressing it as cosine over sine, identifying our u and v functions, finding their derivatives, and substituting everything into the quotient rule formula. Now we have the derivative of cotangent from applying the quotient rule, but it looks quite complex. We can simplify this expression significantly using a fundamental trigonometric identity. The key to simplifying this expression lies in recognizing a pattern in the numerator. Notice that we have negative sine squared of x minus cosine squared of x. We can factor out the negative sign from the numerator. This gives us negative times the quantity sine squared x plus cosine squared x. Now here comes the crucial insight. The expression sine squared x plus cosine squared x is one of the most important identities in trigonometry, the Pythagorean identity. This identity tells us that sine squared plus cosine squared always equals 1, regardless of the value of x. This is a fundamental relationship that comes from the unit circle. Now we can substitute this identity back into our derivative expression. Since sine squared plus cosine squared equals 1, our numerator becomes simply negative 1. This is a much cleaner expression. We now have negative 1 divided by sine squared of x, but we can make this even more elegant by using another trigonometric function. Remember that the cosecant function is defined as 1 divided by sine. Therefore, 1 divided by sine squared is the same as cosecant squared. Now we can write our final answer. The derivative of cotangent x is negative cosecant squared x. This elegant result shows the power of trigonometric identities in calculus. We transformed a complex rational expression into a simple, memorable form using the Pythagorean identity. The key insight was recognizing that sine squared plus cosine squared equals 1, which allowed us to simplify the numerator completely. This is why memorizing fundamental trigonometric identities is so valuable in calculus. Now we shift our focus to one of the most powerful tools in trigonometry, trigonometric identities. Understanding these mathematical relationships will unlock new ways to solve complex problems and simplify expressions. A trigonometric identity is an equality involving trigonometric functions that holds true for all values of the variables for which both sides of the equality are defined. This means no matter what angle you substitute, the equation will always be satisfied. The most famous trigonometric identity is the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. This identity is true for any angle theta you can imagine. We can see why this identity is always true by looking at the unit circle. In a unit circle with radius 1, any point on the circle creates a right triangle where the horizontal distance is cosine theta and the vertical distance is sine theta. By the Pythagorean theorem, the square of the horizontal side plus the square of the vertical side equals the square of the hypotenuse. Since our hypotenuse has length 1, we get cosine squared theta plus sine squared theta equals 1. Trigonometric identities are incredibly important because they allow us to simplify complex expressions, solve equations that would otherwise be impossible, prove mathematical theorems, and they're essential tools in calculus, physics, and engineering applications. Here's a concrete example. If we evaluate sine squared of 30 degrees plus cosine squared of 30 degrees, we can either calculate each value separately and add them, or we can immediately recognize that by our identity, this must equal 1. This demonstrates the power of trigonometric identities. Instead of doing complex calculations every time, we can use these fundamental relationships to immediately simplify expressions and solve problems more efficiently. Now that we understand what trigonometric identities are and why they are so valuable, we're ready to explore the different types of identities and learn how to recognize and apply each one effectively. Now that we understand what trigonometric identities are, we need to explore the different types that exist. There are 6 main categories of trigonometric identities, each serving specific purposes in mathematics. These 6 types cover all the fundamental relationships between trigonometric functions. Each type reveals different patterns and connections that help us solve complex trigonometric problems. The first and most fundamental type are the Pythagorean identities. These come directly from the Pythagorean theorem applied to the unit circle. The most famous Pythagorean identity states that sine squared theta plus cosine squared theta equals 1. This fundamental relationship comes from the unit circle, where the radius always equals 1. The second Pythagorean identity shows that 1 plus tangent squared theta equals secant squared theta. This can be derived by dividing the first identity by cosine squared theta. The third Pythagorean identity states that cosecant squared theta equals 1 plus cotangent squared theta. This comes from dividing the first identity by sine squared theta. The second type are reciprocal identities. These show the relationship between the 6 trigonometric functions and their reciprocals. Cosecant theta equals 1 divided by sine theta. Cosecant is simply the reciprocal of the sine function. Secant theta equals 1 divided by cosine theta. Secant is the reciprocal of the cosine function. Cotangent theta equals 1 divided by tangent theta. Cotangent is the reciprocal of the tangent function. The third type are ratio identities. These express tangent and cotangent in terms of sine and cosine ratios. Tangent theta equals sine theta divided by cosine theta. This comes from the definition of tangent as opposite over adjacent in a right triangle. Cotangent theta equals cosine theta divided by sine theta. This is the reciprocal of the tangent ratio. The fourth type are complementary angle identities. These show relationships when two angles add up to 90 degrees. Sine of 90 degrees minus theta equals cosine theta. This shows that sine and cosine are complementary functions. Cosine of 90 degrees minus theta equals sine theta. This is the reverse of the previous identity. Tangent of 90 degrees minus theta equals cotangent theta. Tangent and cotangent are also complementary functions. The fifth type are supplementary angle identities. These apply when angles are related to 180 degrees. Sine of 180 degrees minus theta equals sine theta. The sine function has symmetry about 90 degrees. Cosine of 180 degrees minus theta equals negative cosine theta. Notice the negative sign appears for cosine. Tangent of 180 degrees minus theta equals negative tangent theta. Tangent also gets a negative sign. The sixth and final type are opposite angle identities. These show what happens when we use negative angles. Sine of negative theta equals negative sine theta. Sine is an odd function, meaning it changes sign when the angle is negated. Cosine of negative theta equals cosine theta. Cosine is an even function, meaning it stays the same when the angle is negated. Tangent of negative theta equals negative tangent theta. Like sine, tangent is also an odd function. These 6 types of trigonometric identities form the foundation for solving complex trigonometric problems. Each type reveals different patterns and relationships that help us understand how trigonometric functions behave under various transformations. Now that we understand trigonometric identities, we need to explore their practical applications and learn helpful memory techniques to master them effectively. Trigonometric identities have 3 main applications in mathematics. First, they help us simplify complex trigonometric expressions into more manageable forms. Second, they are essential tools for solving trigonometric equations by transforming them into forms we can work with more easily. Third, in calculus, they enable us to integrate non-trigonometric functions using trigonometric substitution techniques. The most famous mnemonic for remembering basic trigonometric ratios is SOH CASH TOE. This helps us remember the definitions using a right triangle. SOH stands for sine equals opposite over hypotenuse. This tells us that the sine of an angle is the ratio of the opposite side to the hypotenuse. CAH stands for cosine equals adjacent over hypotenuse. The cosine of an angle is the ratio of the adjacent side to the hypotenuse. TOA stands for tangent equals opposite over adjacent. The tangent of an angle is the ratio of the opposite side to the adjacent side. Our first example demonstrates how identities help simplify expressions. We need to simplify the fraction sine squared x over 1 plus cosine x. Step 1. We use the Pythagorean identity. We know that sine squared x plus cosine squared x equals 1. Rearranging this identity, we get sine squared x equals 1 minus cosine squared x. Step 2, we substitute this identity into our original expression. Sine squared x over 1 plus cosine x becomes 1 minus cosine squared x over 1 plus cosine x. Step 3, we factor the numerator. 1 minus cosine squared x factors as 1 minus cosine x times 1 plus cosine x. Now we can cancel the common factor of 1 plus cosine x, leaving us with the simplified result, 1 minus cosine x. Example 2 shows how identities help solve trigonometric equations. We need to solve 2 sine squared x minus sine x minus 1 equals 0. Step 1, we recognize this as a quadratic equation in sine x. Let u equal sine x, so our equation becomes 2u squared minus u minus 1 equals 0. Step 2, we factor the quadratic. 2u squared minus u minus 1 factors as 2u plus 1 times u minus 1 equals 0. This gives us u equals negative 1/2 or u equals 1. Step 3, we substitute back. Since u equals sine x, we have sine x equals negative 1/2 or sine x equals 1. Using the unit circle, sine x equals negative 1/2 at 7 pi over 6 and 11 pi over 6, while sine x equals 1 at pi over 2 plus any multiple of 2 pi. Our final example demonstrates proving a complex identity. We need to prove that 1 plus cosine x over sine x equals sine x over 1 minus cosine x. Our strategy is to cross-multiply both sides and then use trigonometric identities to show they are equal. Working with the left side, 1 plus cosine x squared expands to 1 plus 2 cosine x plus cosine squared x. For the right side, sine squared x times sine x over 1 minus cosine x simplifies to sine squared x over 1 minus cosine x. Using the Pythagorean identity, sine squared x equals 1 minus cosine squared x, which factors as 1 minus cosine x times 1 plus cosine x. Substituting this into the right side and canceling common factors gives us 1 plus cosine x, which matches our left side. The identity is proven. To master trigonometric identities, remember these key strategies. Use SOH-CAT-TOE for basic ratios, practice simplifying expressions regularly, apply identities systematically when solving equations, and build your understanding through consistent practice and repetition.